Right now, we have a great speaker, a Canberra local. We have Adrian Herrera talking about deobfuscating JavaScript malware. So let's welcome him to the stage.
Cool. Thank you. Thank you for sticking around. And I'll try not to get it into too much of a lunch break with my talk. All right, so yes, as Silvio said, I'm here to talk about JavaScript and specifically deobfuscating ugly JavaScript malware. All right, so a little bit about myself. So I wear two kind of hats in my day job. One hat, I'm a researcher with the Defence Science and Technology group here in Canberra. And my other hat is my academic hat. And I've recently started a PhD at the ANU, also here in Canberra. And my main research is around reverse engineering and applying what's known as program analysis to reverse engineering problems. And today is one example of that. All right, so I'm not a JavaScript dev at all. In fact, I kind of just learned how to write JavaScript this week when I was preparing for this talk. But I'm told that it's very widely used. And there are lots of different frameworks out there, lots of different platforms and tools and things for JavaScript. And that's kind of, oh no, what's happened? Let's bring that back up. Yes, all right, we're back. That's not really the focus of today's talk. What I'm more interested in talking about is this kind of JavaScript, which is a malware sample that does some malicious stuff and has been heavily obfuscated by the author to make the reverse engineering process by the malware analyst really hard. So I've kind of cut the sample off a bit to display it on the slide. But if we look at the full thing here, I can probably make this a bit bigger. This one. This one. Oh, no, not that one. Right, so this is the original sample here. And yeah, it's pretty hard to make sense of. It keeps going on and on and on. And our aim is to apply static analysis to this kind of malware to strip it back to its bare minimum and figure out what it's doing. So yeah, so the ultimate aim is to make this kind of thing more readable to a malware analyst. And so why do we want to do this? Well, if you're a malware analyst, you already kind of know that obfuscation hinders your analysis and makes it harder, makes it more time-consuming, makes it just life a lot tougher. And this is not just true of like JavaScript and scripting languages, but you can obfuscate binaries, and you can obfuscate scripting languages other than JavaScript. So this is, I believe, VB script. It's pretty tricky to read. It's not really clear what it's doing. I guess other than the name start exploit maybe gives you some indication. But other than that, it's kind of tricky to understand what it's doing. And then, of course, there's JavaScript as well. So if I'm a malware author and I want to make it hard for the analyst, I would apply all these different kinds of obfuscation techniques. And we want to kind of undo all of that work. All right, so the approach that I took when building a tool for deobfuscating JavaScript was to borrow a bunch of ideas from compiler theory and apply them to the deobfuscation process. And so a bit different to compiler theory, instead with compilers, we're trying to generate executable code at the end of it. Here we're trying to essentially get more readable source code instead. And so what else are our goals? So I've got here, focus on semantic transformations. And what I mean by this is that we can, there are a bunch of tools already out there that allow us to pretty print source code. So one of them for JavaScript is Uglify.js, which is the one I kind of accidentally did before. And so by pretty printing, I mean inserting white space, indentation, new lines to make it more easier to read, but it's still kind of hard to figure out what it's doing. There's still a lot of code there to try and get an understanding of. So we're not really interested in that. What we're interested in is doing some more, I guess, interesting transformations to make this more readable. And we want to reuse a bunch of existing tools. All right, so for those who haven't studied compilers before, or for those who have, maybe you've seen a similar kind of diagram to this in a compiler's course. But this is a typical compiler workflow. It starts with the lexer, or the tokenizer, which takes your source code, breaks it up into tokens, and assigns some kind of category to those tokens. So maybe you've got tokens for white space, you've got tokens for keywords, you've got tokens for variable names, etc. And then that stream of tokens goes into the parser, and the parser does some more kind of analysis on that and generates a parse tree based on some kind of grammar. And then from that parse tree, we can strip away the uninteresting things, like white space, for example, and we get an AST, or an abstract syntax tree, which Pat mentioned in his first talk of today. And then on that AST, we can apply various optimizations. And for a compiler, the aim of those optimizations is to produce either smaller code or faster code. And so there are a bunch of different tricks that compilers use to do this. And then after we've done that, we want to generate executable machine code. So that's kind of a typical compiler workflow. Now, how can we apply this to deobfuscation? Well, it's pretty similar. So here's another diagram. We've got 3 of the same 4 elements that we saw in the previous slide. So we still got a lexer, we still got a parser. Instead of a code generator at the end, we just want to generate source code back out again. And now, instead of optimizing for speed or size, we kind of want to optimize, in a sense, for readability. So this is essentially what deobfuscation is. And the nice thing about reusing this kind of workflow is there are already a bunch of existing tools that give us parsers and lexers and generators for various kind of languages, including JavaScript. All right, so I kind of touched on this before, but the lexer turns the characters into words, and then the parser is kind of the interesting thing. So we take those stream of words, we generate a parse tree according to some grammar, and then we discard a bunch of uninteresting things to get the AST. And then what we want to do is we want to apply some sort of analysis and some sort of transformations on the AST to do our deobfuscation. All right, so the tool that I based my work on is this one. It's called SAFE. It's out of a research group in South Korea. It's essentially a JavaScript analysis framework. It was not really made for the purposes of security, but just for generic analysis of JavaScript code. And it already gives us the things that we kind of need. So it gives us the lexer, it gives us the parser, it gives us the source generator. It also gives us a bunch of intermediate representations, so we can go do different kinds of analyses on top of those IRs. But in the end, I didn't end up using that kind of stuff. All right, so this is a snippet of the sample we saw at the beginning. Again, chosen so I can fit it on a single slide. And this has been pre-printed with Uglify.js. And so what we can do is we can run safe over this to generate an AST and kind of do some analyses on that AST. All right, so this is what the AST would look like if we were to visualize it as a tree, because that's all it is. And I've got it here as well, interactively. And so we can kind of look at the source code here. So this is the same source code on the left, and the AST is on the right. And we can kind of match up the different elements in the source code to the nodes in the tree. So at the top level, we have our entire program. Our program is made up of a number of source elements. These are 2 variables, which are these 2 here, plus this if statement here. And we can continue expanding out different elements of the tree. So this variable is this one here, and it's been assigned the undefined value, and so on. All right, so let's look at actually, I guess, the meat of this work, and that is how we build a deobfuscator to do things to this AST. So if you're familiar with compilers, again, many of these kind of terms may look familiar. So these are typical compiler optimization techniques, and it turns out that we can reuse a bunch of them to make code easier to read as well. So I'm not going to talk about all of them today. I'll just talk about a subset of them because of time, which are the 3 highlighted here. And what we essentially do in our deobfuscator is we keep running and applying these different transformations over the top of our AST until the tree stops changing, or we've reached a fixed point. And at that point, we can kind of serialize the tree back to source code. And hopefully, at the end of it, we've got more readable code. All right, so let's start with the simplest optimization, which is constant folding. And so what constant folding does is it looks for constant expressions in code and then just evaluates them statically rather than waiting for the code to run and to evaluate at runtime. So if we go back to our example here and we change to this one. So if we look at our code here, we can, hopefully you can see a bunch of places where we can kind of pre-evaluate what the result will be without actually having to run the code. So for example, in this if expression here, we've got these 3 strings concatenated together. But what we can do is we can just pre-compute this rather than doing this at runtime and just get a single string, which is easier to read. And the other location is this one here. So we have these 2 integers added together. And once again, we can just combine them and spit out new code with the combined or the added value of those 2 numbers. So if we look at the tree and figure out how we're going to do this, so if we look at this if statement here, what that looks like in AST form, we can see the tree in the if statement is made up of these 2 subtrees, I guess, which consists of 2 operations, which are the addition or the concatenation, I guess, because they're strings. And then we can see on either side of that operation, we have 2 string literals. And so if we recognize that pattern while we're walking the tree, then we can essentially just perform that operation and replace this subtree here, consisting of these 3 nodes, with a single node, which is the concatenation of those 2 strings. All right, so the slides kind of just repeat what I just said. So here's the tree again. And so we're running our deobfuscator. It's walking the tree. It sees this kind of pattern. And it says, well, they're just 2 string literals. I can pre-compute the final value of that. And then we get undefined. And then what happens is we get a new subtree. And once again, we can pre-compute the result of that. And we get a simplified string. So very simple technique. But it makes things slightly more readable. So it's not just strings that we can do this to. We can do this for integers. So again, in the code, we had 100 plus 88. So we can pre-compute that and get 188. And because JavaScript's a terrible language and it lets us do very terrible things, we can have all sorts of different operations on different types of data. So for the top one here, we have a string and then an int. And so what happens, if you're a JavaScript person, you probably know that the int becomes a string, and then we get a string at the end of it. What about this one here? If we have 10 minus true, so true becomes an integer, value 1, and then we have 10 minus 1, so we can replace that with 9. Not 1 is 0, times it by a float, we get 0. And this one here is the same as the top one, just the types are reversed, but it's still, we end up with a string. And so we can encode all these rules in our deobfuscator when we walk the tree, and we just look for nodes that contain these types. And we look up our rules, and we say, oh, OK, we can just replace this node with a simpler node. And to do this, we kind of have to understand what these operations mean. So in this one, this operator here means plus, but for strings, it means concatenation. And so this kind of requires, I guess my point here is that it requires understanding of the semantics, or what it actually means when you see this operator in your code. All right, so going back to our example. So we run that, and we get these collapsed strings here. All right, so how do we implement it? I guess I've already described this. We write a bunch of rules. We start with our root node in the tree. We walk the tree, and we just apply the rules to get simplified nodes. And then we just keep recursing until, again, we reach a fixed point. All right, so that's constant folding. A slightly different technique is constant propagation. And so constant folding looks for 2 literals with some operation applied to them. Constant propagation is that we know that a variable can only ever hold 1 value, and therefore we can just replace every use of that variable with that value. So here's our code again. And if we look closely, we can find some instances of where we can do this propagation, which are here. So in this function at the top, we have this variable here, which is set to null. And then the only time that variable is ever used is this just returned from that function. And so we can kind of, again, recognize this pattern in the tree and just remove this variable and have the function just return null. Similarly here, this variable here is only written to up here. It's set to undefined, and it's not written to anywhere else in the code. And so once again, we can just replace that variable altogether. All right, so this is the substitution step. So we substitute those variables values where they're used, and then we can just delete those unused variables. So once again, we've removed a bunch of code with the aim of getting easier code to read. And the other benefit of this is that we can now start to see where we can reapply some of our the previous technique, constant folding, because we've now got a simpler AST. So for example, here, we can make a rule in our constant folder to say that the type of undefined is the string undefined, and so we can replace that. And then we can have another rule that says if we have two strings on top of a equality, then we can just collapse that to true. And then if we have if true, then we know that that will always be the case, so we can just remove the if condition altogether. So by building these simple primitives, we can keep applying them and stripping away the code to the bare minimum. All right, and then we delete the unused variables. All right, so constant propagation is a pretty easy idea to get your head around. The implementation compared to constant folding is a bit more trickier. You have to pass over the AST a number of times, one to propagate the constants, and then go back and look for redundant assignments and remove them. And because I'm a program analysis nerd, this is implemented as an abstract interpretation, which I won't go into the details of that today. All right. And so the third trick that I wanted to talk about is function inlining. So this is another pretty easy one. It's kind of obvious when you look at it. So now we have this function here. It doesn't do anything except for return null. And so we can just replace any calls to this function with the value that it returns, which we know is always going to be null. And then we can just delete that function altogether. All right, so it's called here in the switch statement. And we know it's always going to be null. So we can expand it to that value that it returns. And then we can just remove this function because it's no longer called anywhere in the program. And so once again, we've got even less code to look at. And again, we can apply other techniques. So if we're switching on null or on a constant value, then any of the other cases in our switch statement, they can never execute. And so we can just delete them altogether because they're essentially meaningless. They're all dead code. All right, so function inlining, again, kind of easy to implement. You just find you define what it means to be inlineable. So for me, I guess I took the simplest path, which is if a function only contains a single return statement, and that return statement only returns a literal expression, then we consider that to be inlineable. And then so once we've collected all those functions, again, we can just walk the tree and find where those functions are called and just replace it with the value that it returns. So if we go back to our example, where's my tree gone? All right, doesn't matter. And then we keep recursing until we reach the fixed point. All right, so I've talked about three kind of easy compiler optimizations. There are a bunch more we can also talk about. But essentially, the aim is just to remove as much dead code as possible. And by applying different ones, they enable us to remove dead code that appears with another kind of optimization. All right, so let's go back to our malware that we were looking at before, which is this one. And so, so we can see that there's a lot of code here. There's a lot of functions that just return, single values. So we can apply our function inlining to them. There are a bunch of variables here that only get assigned a single value, so we can propagate those values throughout the code, and we keep doing different things until we can't go any further. So let's run the tool on top of that code. So safe is the tool, and then I've just added a deobfuscate subcommand to it, and then we give it, the JavaScript file that we want and the output file that we want it to go to, and then we run it, and then we get, it terminates hopefully, and then we can look at it and see what we get. So now we had 460 odd lines of code before, and now we've reduced it down to 11. So we've done a bunch of extra things here. So I've renamed variables to make them more memorable. So I just picked animal names. So that's why we've got these funky animals all throughout the code. But now, hopefully, we've got JavaScript that is much easier to understand what it's doing, because we've stripped away all the cruft that really had no effect on the malware at all. All right, so this is the same kind of slides here. So we started with 680 lines of code when it was pretty printed. And then once we deobfuscate it, we reduce it down to 11 lines of code. And congratulations, if you're the malware analyst, now you have obfuscated PowerShell inside it that you have to deobfuscate. But again, these techniques are kind of generic, and you could, in theory, build a static analysis for PowerShell and do the exact same thing. So this sample just happened to have PowerShell in it, but I've tried this on a bunch of other samples, and it has a similar effect. It deletes lots of code, and you kind of makes it much easier to read. All right, cool. So by looking at ideas from compilers, we can build some pretty powerful tools, such as a deobfuscator. This idea is not really that new, but it's kind of effective, I guess, for malware analysts. And it's applicable across different kind of languages, not just JavaScript. So as long as you can generate, as long as you have a parser for a language that gives you AST that you can walk and transform, then you can essentially apply these techniques to that AST to reduce it down to something more meaningful. And yeah, I guess that's a summary. That's the end of my talk. Thank you very much.